So here is another nice work problem from Calculus 2. So here we're going to be looking for the work required to pull the rope to the top of the building. Uh, Definitely we're going to want to draw a little picture of our situation. So let me draw here my building. There's my building. And now the way that you orient your picture is going to change the way you solve a little bit. And the way I always do it is you'll see if you watch my video on finding the work required to pump the water out of a tank, I orient it so the top of the tank is 0. And I'm going to do the same thing here. So the top here of my building is going to be 0. And then as I extend down, X increases. Okay. So my rope is 10 feet long. So I'll make this the bottom of my rope. And now let's kind of discuss how we're going to solve the problem. So I'd like to figure out the work required to pull this entire rope to the top of the building. And what I'm going to think about is how we find the area under a curve. So say this is my curve here, and I want to find the area under my curve. Remember the idea behind this is that we're going to slice it up into really tiny slices as small as we can, and then we'll add up the area of all of the slices. And so I'm going to do something very similar except with work. And so on this rope, I'm going to take a sample slice, which is just going to be an interval of my rope. Now this interval here is going to have length delta x. And remember, delta x is that value that we're going to let get really, really tiny. And in my interval, I'll have some point, which I'll just call xi. It's really more appropriate to call it xi star because usually xi is one of the ends of the interval. But I just don't feel like writing the star over and over again. So we're just going to call it xi. And so what do I need to find? Well, I'm looking for the total work, but first I'm going to find the work just to move one of my slices. And so here I need to find the force per slice times the distance per slice, right? Work is force times distance. Now my force is going to be my force per foot, but then that's a little bit of a problem because my interval is supposed to be really, really small. It's probably not a foot long. So I have my force per foot, and then to find the force just on my interval, I'm going to multiply it by the length of my interval or the length of my slice. I'll say the length of interval. And I have to multiply this by the distance per slice. Okay. So my force per foot is going to be my 50 pounds divided by the length of my rope. Now the length of my interval we specified at the beginning is delta x. And then what do I mean by distance? What my distance here means is how far my slice has to travel to get to the top of the building. So by the way I oriented this, I have to travel xi units to get to the top. So I'm going to multiply by xi. And so the work for a single slice is going to be 5xi delta x. It's always going to be nice to just put your delta x at the end. Now, the way these problems usually get set up in a Calc 2 course is that you set it up as a Riemann sum. And so that's the way I'm solving the problem. And so then my total work, again, similarly to how we do the area under a curve, I am going to add up all of the work on my slices. So I'll put 5xi delta x. And let's just say we have n slices. But then we want our slices to be really, really, really small. In fact, as small as they can possibly be so that we get the perfect total of work. And so I'm going to take the limit as n approaches infinity, which is just going to let our slices shrink smaller and smaller and smaller and smaller. But this is just the definition of our Riemann integral. And so we're going to integrate 5x dx. And we need to integrate from 0 to 10, the full length of my rope. So we have 5x squared over 2 from 0 to 10. So we should just get 5 halves times 100, which is 250. Now, once again, if you've watched any of my other videos, I am very bad about my units. I just don't keep them throughout the whole problem, and then I throw them in at the end. So we are in like US standard units, and we're calculating work, so this should be foot pounds. Okay. And that was just for the first problem. So it asked us how much work is required to lift, the entire rope to the top. Now, the second problem asked how much work is required to lift half the rope to the top. Now, before we solve this, I just want to discuss it really quickly. So what's tempting to some students is to say, oh, well, if it was 250 for the entire rope, it should be 125, half for half the rope. But let's think about why that is not accurate. So when we start pulling up the rope, we have 10 feet hanging down, which is, adding on weight. It's adding on, we have to do more work. Once I pulled up, say, half the rope, well, now I have a lot less hanging over the edge. And so it gets easier. The more I pull up the rope, the easier it gets because it weighs less and less as I keep pulling it up. So we expect that the first half to pull up is actually more difficult than pulling up the second half. And so I do imagine that my answer is going to be more than half of 250. So when you get that as your answer, you shouldn't be surprised that it's more than half. It actually makes sense when you think about it physically. So let's go ahead and start this problem. So this one is to pull up half. What I'm going to do here is split this into two different situations, or two parts. The first is to pull up the top half, and then we're going to look at the bottom half. I'm going to look at these separately and then add them together. So first, let's start with the work required to just pull up the top half. I'll say pretending that the bottom half doesn't exist. So if I pretend that the bottom 5 feet just isn't even there, so it just stops, halfway down, then this should be exactly the same as I did for the first problem. And so I can just steal that answer. So my work here is still 5xi delta x, because it should have been just the exact same thing I did at the beginning. But that isn't all the work. Well, why? Well, by doing this, I've just pretended that the bottom half doesn't even exist. So I'll say that isn't all, because I'll just say the bottom half still has weight. And of course, should add work to the total work. So we can't just totally ignore the bottom half. And so let's find the work that we need for the bottom. Now I'm going to do this all over again. So it should be the force per foot times the length of my interval times the distance that my slices would move, okay? So let's see where this differs from the original problem. The force per foot should be the same. The rope still weighs the same, it still has the same length, so that's still gonna be 5, 50 divided by 10. The length of my interval is still delta x, and so it must be this d slice that changes. So let's come up and look here what happens. So I'm wondering what happens to just the bottom half. Let's say this is my bottom half. It doesn't get pulled up to the top, not quite, right? We don't pull everything up to the top, but the bottom half essentially replaces the top half, right? If I pull the top half up to the top of the building, then the bottom half replaces where the top half was. And so no matter what slice I take, everything should have moved up 5 feet. And so it's no longer xi, it's just 5. Everything moves up 5 feet. And so I just get 25 delta x. And now I can put everything together. So this is going to be my sum. And I need to add these two things together. So I have the 5xi delta x, and I'm going to add 25 delta x. And again, we're really setting up our Riemann sum. So take our limits as n goes to infinity. And I'll rewrite this a little bit just so delta x is at the end. So we do have a delta x in both terms, and so I'm just going to factor it out and put it at the end. And now this is just the definition of our Riemann integral, and so I can write this as 5x plus 25 dx. Now, what do I need to integrate from? Well, I'm only pulling up the top half, and so I can just integrate from 0 to 5. Now, you might be thinking, oh, I thought we weren't supposed to ignore the bottom half. Well, I didn't. This plus 25 has incorporated the work necessary to also have that weight of the bottom half, so we're good to go. Then we have a 5x squared over 2 plus 25x from 0 to 5. And now notice when I evaluate at the lower limit of 0, I would just get 0 plus 0. So I'm just going to put in the 5. So I'll have a 5 times 25 over 2 plus 25 times 5, which is 125 over 2 plus 125. And so we get 187.5 foot-pounds.